In this video, you're going to learn how to send encrypted messages from Polygon testnet to Secret Network testnet, where the messages are then decrypted in Secret Network smart contracts. And we're going to be using a combination of Solidity, Rust, and Axelar GMP. If you're an Ethereum developer who's never worked with secret contracts before, or you're a secret developer who's never worked with Ethereum contracts before, this video is for you. We're going to walk through every single step from uploading and instantiating contracts on Polygon as well as Secret. I'm going to walk you through the encryption scheme, and I'm also going to walk you through the Axelar GMP portion where we learn how to send cross-chain messages from Ethereum to the Cosmos. So everything we're going to be doing today, it all goes back to this one page of the Secret Network docs, which is part of the Ethereum Virtual Machine Developer Toolkit. And the page that we're working with is called EVM Encryption Decryption with Secret Contracts. Basically, what we're going to be learning how to do is any sort of message you want to be able to send on Ethereum or you want to keep that message private, that is now possible with Secret Network smart contracts. Any sort of transaction you can imagine on Ethereum can now be encrypted and then decrypted in a Secret Network smart contract. That's what we're going to be learning today. And basically what we're doing is generating a public and private key pair in our front end as well as in our Secret Network smart contract. And then through a key exchange protocol called elliptic curve Diffie-Hellman, what we're doing is using the public and private keys that we generate both on our front end and in our Secret Network smart contract to generate a shared secret, is what it's called. And that's what we're using to be able to encrypt and decrypt our messages from our front end, from our Polygon contract to our Secret Network smart contract. So let's just dive into the code, and if you have any questions, just drop them in the comments below this YouTube video, and I will be sure to respond to them. The very first thing that we're going to do is we're going to clone down this Secret Network repo. It's the Secret Labs examples repo. This is a repo that Secret Labs, the development team behind Secret Network, hosts, which just has a bunch of different developer tutorial examples, and they all link back to the Secret developer docs. So if you want to learn more after this video, other ways of working with privacy preserving contracts, definitely check out this repository, which I will be sure to link in the video description below. So the example repo that we're going to be working with today is this EVM encrypt decrypt. And you'll see that if we look at the folder structure, there's two pieces to it. There's the Polygon contract, and there's also the Secret Network contract. And we're going to start by just installing the dependencies for the Polygon contract. So let's cd into EVM encrypt decrypt Polygon. So now I'm in this Polygon folder, and the first thing we're going to do is just install those dependencies by running npm I or npm install. And while we're waiting for our dependencies to install, the next step that we have to do is just build out our environment variables. So we have three different environment variables that we need to be able to work with these two smart contracts we're going to be working with today. We need the private key of an Ethereum wallet. We need an Infura API key. And we also need our mnemonic phrase for our Secret Network wallet. So in order to get these environment variables, we need to have both a Kepler wallet and a MetaMask wallet so that we can have our private keys for Secret Network as well as for Polygon. So let's do that real quick. Let's first just start by downloading MetaMask. So I'm just going to add this to Chrome. All right. While we're at it, we'll also just download Kepler. Kepler is just like MetaMask, but for the Cosmos. We're going to create a new wallet. Now we have this wallet created. The next thing we're going to want to do is just add Polygon testnet to our wallet. What we need to do is three things now. We need to export our private key so we have access to it in our code editor. We also need to fund our wallet with Polygon testnet tokens, and we also need to add the Polygon testnet to our MetaMask wallet. So we're going to do all three of those things right now. First off, let's just export our private key. So if you click these three dots and then go to account details, you can say show private key. You'll be prompted to enter your password, confirm, hold to reveal private key. And this is all information you would never want to show on a stream or to anyone. This is just for testing purposes. I'm only going to fund this with testnet tokens, which is why we're doing this. And I just want to make sure you understand how to do this, but you would never show your private key normally. So I'm going to copy that private key variable. I'm going to go back into VS Code, paste that in here. Great. Next, we need to add Polygon testnet to our MetaMask wallet. And we're going to do that by adding a network manually in our MetaMask wallet. So the way we do that is you click your network here, click Add Network, scroll down. If you don't see the network here, which we don't because we're trying to add Polygon testnet, we can say Add a Network manually. And then we say the network name, new RPC URL, chain ID, etc. And if you go to Polygon's docs, you can get all the information that we need to add here. So we're just going to do that, paste that in. Great. So now we have that. And next step, we have to fund that wallet. Let's just go to a faucet, which this is also linked in the Secret Network docs. I'm at faucet.polygon.technology. And I just need to paste in my Matic address. So I'm going to copy that here from MetaMask. So the next step is we should create a new Kepler wallet for our Secret Network wallet. So let's create a new recovery phrase. Again, don't show this with anybody. Now we just need to add Secret Network testnet and fund our Secret Network testnet wallet, which we can do by going to this page of the Secret Network docs using the testnet if you've never done this before. So we're going to click this link right here, which will add Secret Network testnet to our Kepler wallet. Bam, and we currently have 0 secret. Now let's just fund that wallet, which we can just do by using this faucet right here. And if you don't see secret testnet in your available balances, what you might have to do is click on this up here, go to Manage Chain Visibility, search for secret, and there we go, add Secret Network testnet like that, click Save. And now when we go back, we'll see secret testnet here. Let's copy our wallet address. So just like that, go back to the faucet, confirm you're not a robot, and click Continue. And Secret is less stingy with their testnet tokens. They send you 100 tokens instead of 0.2. I don't know what the Matic people are doing over there, but that's how it be. Now what we got to do is just take those words from Kepler, your private mnemonic words, and paste them into the environment file, because that's what we're going to use to access our Secret Network testnet wallet. So if we go back to our code, enter those words there. So now we have our EVM, our Polygon testnet private key, we have our Secret Network mnemonic. And the last thing we need is our Infura key, which is going to allow us to upload and instantiate and execute our Polygon contract. So let's get that really quickly by just going to Infura. You just go to Get Started. And then if you haven't already, you just create a new API key, name, and we want this for Polygon Mumbai. And there's my key, right? So take that, paste it in, and now our environment is totally configured and we're good to go for the rest of this tutorial. All right, so now we've created our Secret Network wallet, we've created our Polygon Mumbai wallet, we've gotten our Infura API key, and we've installed our Polygon dependencies. We are now ready to go to start uploading and instantiating our Polygon testnet contract. So the first step that we need to do now is actually deploy our Polygon contract, and we can do that by running npx hardhat compile. All right, great. Our 6 Solidity files were successfully compiled. And if you want to see what that's actually doing behind the scenes, so if we go into this Polygon folder, what we will see is that we have a contracts folder, and in that we have this send receive encrypt.sol file. And this is actually our Axelar Solidity smart contract that allows us to send a message from Polygon testnet or Polygon mainnet, if we were to deploy it to mainnet, to Secret Network, right? And if we look at our contract, what we actually have here, it's extremely simple. All of this happens in just 100 lines of code. And what this allows us to do is send a message from Polygon to Secret using Axelar GMP. And the main thing to note here is that in our constructor, we have 3 parameters. We have a gateway parameter, a gas receiver parameter, and a chain name parameter. And we will come back to all of that momentarily. So our contract is now successfully compiled. The next step is to actually just deploy the contract to Polygon testnet. And that's all possible because we just added all those variables to our environment variable. And the reason we need these is for our hard hat config. So if we look in here and we see that we have this configured for Polygon testnet, this is where our Infura private key is, and this is where our private key is for our wallet. This is what actually allows us to upload and execute the smart contract. To deploy, we're just going to run the deploy script, which is npx hardhat run scripts/deploy. And we specify the network, which is Polygon, because we specified that here in our hardhat config file. And the script that's actually being run there, if you want to look at that behind the scenes, is if we go into the scripts folder and deploy.js, this is very important to understand. These are the constructors that I just mentioned in the Solidity contract. We have our Axelar gateway contract, our Axelar gas service contract, and our chain name, which is Polygon. So just for reference, for anyone who's maybe working with Axelar GMP for the very first time, I want you to understand how this works. If you go to Axelar's docs, to this developers tab, and then scroll down to here, reference, we have mainnet chain names as well as testnet chain names. So these are the 3 parameters that we're adding. Polygon, right? We need to specify that we're using Polygon testnet, and then we have these testnet contract addresses. And they have them for all of these EVM compatible chains, right? But here's our gateway contract address. Here's our gas service contract address. This is what we are instantiating our Solidity contract with, is these variables here. If you wanted to do this with Gurley testnet or BNB or Avalanche or Moonbase, etc., all of those variables are here. You would just need to use these gateway and gas service contracts and those testnet chain names. And if you wanted to do this on mainnet, you could literally do that with mainnet by just using those chain names and contract addresses. Great. So let us run this script now and see what happens. Amazing. So our send, receive, encrypt contract has now been deployed to this address. And if you run into any error here, just make sure that when you created your Infura key and you added Polygon Mumbai, that you saved those changes. Because I've ran into an error before where I forgot to save the changes and then the endpoint didn't work. But if your endpoint is correct, then you should be able to deploy this contract. So now let's just check this out real quick with the Polygon Explorer just to see that it exists. All right, so we're at the mumbai.polygonscan.com Explorer. I'm just going to search that contract address and make sure that it's returned. And here we go. This is our smart contract. It's now uploaded and instantiated on Polygon testnet. Now that we've done that, we are ready to send an encrypted message from Polygon testnet to Secret Network. Let's just get our Secret Network contract uploaded and instantiated so that it can receive our encrypted message. So what we want to do now, we're going to create a new window in our terminal, and now we're going to cd into EVM encrypt decrypt /secret network. So let's close out our Polygon folder for a sec, check out the Secret Network folder. The first thing we're going to do is compile our smart contract, and this is a little bit different with Rust. All we need to do is run make build mainnet. And what this does is it takes this make file and it runs this script here to compile our WASM file. If you've never worked with a Rust smart contract before with COSM WASM, you might need to install make to your system to be able to run make build mainnet. So if you run into an error, you might just have to install make. Just want to flag that. I've already installed make, so I'm going to run make build mainnet. And what it's going to do is compile our smart contract. Let's check it out. So our contract is built up of these various components. If we actually go to the contract RS file, we'll see our instantiate script, and then what the contract can actually do is in this execute function, we can create keys, we can decrypt a message with try decrypt, and we can receive a message from the EVM. So basically all the smart contract is doing is it can receive our encrypted message from our Solidity contract that we uploaded to Polygon testnet. It can also create keys because we have to be able to generate our private public key pair in order to decrypt the message that we receive from our Polygon smart contract. And it can decrypt the message that we receive with this try decrypt function. So here's our create keys function. We're not going to get into the nitty gritty, but all that you need to know is that it uses the elliptic curve cryptography in order to generate our keys, and it creates a public and private key pair and then saves them to our smart contract into this myKeys variable. And then we are able to query those keys, and what is returned is just our public key but never our private key. All right, so our contract has successfully compiled. Let's just install the dependencies that we need for our secret contract to actually upload and instantiate it. So we're going to cd into node, and then once again run npm install. All right, so now everything that's in our package.json has been installed in our secret network node folder, this right here. And now we're ready to upload and instantiate our smart contract. And all of that happens in this node folder in our index.js file. If we take a look at this, this is what is actually uploading. We have our upload function, and we have our instantiate function. And unlike the Ethereum contract, the Polygon contract, we have no parameters that are needed to be included in our instantiate script. So we can just instantiate the contract as is. So let's do this. Let's run node index. It's going to say starting deployment. And it returns a code ID and a contract hash, which is then used to instantiate the contract and return our contract address. Amazing. So now we have a smart contract uploaded and instantiated on Polygon testnet as well as Secret Network testnet. Now to actually encrypt our message on Polygon testnet, what we need is the public key from our Secret Network smart contract. So let's generate the public-private key pair in the secret contract and then share that public key with our front end so that we can encrypt our message that we're going to send from Polygon to Secret. And we do that with this create keys script, which I wrote. So all this is doing is generating our key pair, and the way it does that is by executing that message that I was showing earlier in contract RS. So it's just executing this try create keys function and then saving our key pair to our contract so that we can query the public key and use that to encrypt our message for our Polygon contract. So it sounds more complicated than it is because all we got to do is run node create keys. Great. It looks like our transaction was executed successfully. And if we want to query our keys, we can do that with node get keys. Again, that's just in here in our scripts that we have. And what it should do is return our public key. Awesome. And we can see that there's our public key that we just generated. Now let's use this public key to encrypt a message in our Polygon smart contract. Now we're going to go back to the Polygon window in our terminal. And we're going to open up this Encrypt.js file. Let me close the secret network folder. We're going to check out our scripts. So we already ran deploy. Now we're going to run encrypt. This is where a lot of the magic happens, and I don't want to go too far into it, but the main thing for you to know is that right now I just have hard-coded our secret public key. So let's just pull that from here. We just queried that key, right? So you take that and then just replace that with the public key that's currently in the repository with your public key that you generated that's unique to you. Awesome. And if you wanted, what you could do with this is you could actually use scrt.network to query the public key. We're not going to do that right now. We're just going to hard code it, but know that that is an option. So now we use this secret public key and the public private key pair that we generate in JavaScript using this library here, this elliptic curve library, in order to create our shared secret and then encrypt our message using AES cryptography. And then we're going to send that encrypted message from Polygon to secret. This file, encrypt.js, is where all of the magic actually happens for the encryption. And it might look kind of scary, right? There's a lot of code here. There's a lot of stuff going on. But the great thing is that in order to experiment and test with this, you only need to change 3 or 4 lines of code with your specific parameters. So let's do that right now. So the first thing you need to do is just change this secret public key to your public key. So I took the public key from that I just generated here, and I just pasted that in here so that I'm working with the public key that is specific to my secret network smart contract. The next thing that we need to do is update our send receive encrypt address as well as our destination address. So this here, send receive encrypt, this is the address of our Polygon contract. So let's just take that. We said we deployed it here. So we're going to take our contract address, I'm going to copy that, and I'm going to paste it here. The chain still remains the same. The destination chain where we're sending the message to is still secret, and the destination address is just our contract address, which we deployed just a few minutes ago. So I'm going to copy that and replace that here. All right, so once you've updated the secret public key with your secret public key, as well as the Polygon contract address with your Polygon contract address, and the secret contract address with your secret contract address, all that's left to do is write the message that you want to encrypt. So we're just going to encrypt this object here that says hello world. I'm just going to add my initials for funsies, and you can make this message whatever you want. All that matters is that it's an object, and that's what we're going to be encrypting and then decrypting in our secret network smart contract. So I've updated my message. So now all that's left is to actually encrypt the transaction. Let's do it. And the way we do that is by running the command npx hardhat network polygon run scripts encrypt.js. Going to run that. And what we see returned is the encrypted data in an array, as well as a transaction hash and a message that says the send function executed successfully, which is what we should see logged upon successful execution. So now let's just check this out on Polygon scan as well as Axelar scan so we can monitor the success of the transaction. So this is our transaction hash, OX56F. And now if we go back to our contract, we should see a most recent transaction. Here we go, 28 seconds ago. And that transaction hash is the exact same that's returned in our terminal. And then if we go to Axelar scan, so this is the way you do this. When you go to Axelar scan, you can toggle back and forth between mainnet and testnet up here. We want to be on testnet. And then we want to go to general message passing from interchain transactions. Great. We'll see our most recent transaction right here. And we see that it was a success being transferred from Axelar scan. Note here that the base fee was 0.41 Matic. So if you don't have enough gas to pay for the transaction, you might have to update that here with this value to be able to pay for Axelar gas to actually execute the transaction. If it says not enough in the base fee, that's what that means. You just update this value accordingly. And now all that's left is to wait for finality. So it says we've got about 3.5 minutes remaining. Let's just wait that out and see what happens. All right, so now if I refresh Axelar scan, it's been about 5 minutes, we'll see that the transaction has been confirmed and executed. So let's jump back into our secret network smart contract in order to decrypt that message that we sent and see that it has been decrypted successfully. So this decrypt function is doing a lot of things. One of the things that it's doing is calling this get stored message, because what the secret smart contract is actually doing is just receiving the encrypted message, and then we call the decrypt function, which decrypts the stored message in the contract and returns the decrypted message. But let's just break this down into smaller parts really quickly so you can see that we have the exact same stored message in the secret contract that we initially sent from Polygon. So if we go back to our terminal, we'll see this is the encrypted message we sent, right? This array here. So when we call get stored message, which all that's doing is in our secret contract, if we go back to the contract itself, this is just returning the stored message that has been received in the contract. And that message gets stored whenever the secret contract receives a message from our EVM smart contract, and that's all happening in this receive message EVM function. So it decodes the message that we receive from Axelar and then saves it to this stored message variable, and then we can use this query function in order to get the stored message response. So let's just do that really quick. I've commented out these other functions for now, like the actual decryption, so that we're just returning this to make sure that it's the same array that we would expect to receive from the EVM. Got to make sure I'm in the right folder directory. So now I'm in Secret Network node, which is where this file exists. The message is received as a hex string, but what we want to do is convert that to a byte array. So let's just do that really quickly so that we can see that our byte array is the exact same as what we sent. And I did that with just this like small little JavaScript function so we can see this together. So I'm going to console log the byte array, which is just taking this query, it's taking that hex string and then converting it to a byte array. I'm going to run it one more time. All right, 244, 153, 54, 146 should be the same in our Polygon. Yep. So it's the exact same encrypted message. So what we see now is that we're working with the same encrypted message, that Axelar successfully relayed the message from our Solidity contract on Polygon testnet to Secret Network testnet. Amazing, right? And now let's use Secret Network contracts to actually decrypt the message that we sent cross-chain. So let's say that the message we sent was like super private. We wanted nobody to know what it was, and that's why we had to encrypt it. Now let's actually decrypt that message. So what I'm going to do is comment out this log. I'm going to return this byte array because that's what we're actually using in our decrypt function. I'm going to leave this commented out, and we're going to comment back the try decrypt function. This is where the decryption is actually happening. So all that's happening in this JavaScript function is we get the encrypted data, right? So using secret.js, we're calling this function get stored message right here, and that's our encrypted data as a byte array. And then we decrypt the data, right? So that this is the data. We decrypt that data and we include the public key from our front end in order to decrypt it, because that's how we generate the shared secret in order to decrypt it in our decrypt function. And if that sounds confusing, let me just take you back to the contract code really quickly so you can see the decrypt function. All right, so this is the decrypt function that we're calling. Note that it takes these two variables, the ciphertext, which is this byte array, and the public key. So this is the public key from the other contract. Or this is the public key from our front end. And this public key, it's saved into our environment variable here when we generated it. And that's all that we're using here. You could hard code it in here, however you want to do that. You could query it. You just want to make sure that you have the public key that we used to send the encrypted message initially. All right, so all this is doing is it's taking the other public key from the front end. It's accessing the private key that's stored privately or securely in our secret contract, and then it's using the other public key and our secret private key to generate a shared secret. And then we're able to use this decrypt function, which takes that shared secret, the ciphertext, which is our encrypted data, and this additional data parameter or variable, which is just something that is needed for this decryption in terms of like the data structure. Okay, and then upon successful decryption, what it should do is return our decrypted data using that shared secret. So let's do that. All right. I'm now going to call try decrypt, which is the function we were just looking at in our contract. And I'm going to comment out get stored message because the only function that we actually want to be calling right now is try decrypt. Oh, and the last thing to notice is that this get decrypted, this is just the decrypted message, which is then saved into the contract after we decrypt it. So at the end of this function here, we call get decrypted to return the decrypted stored variable. Let's check it out. I'm going to run no decrypt once again. There you go. Here's our decrypted variable. Hello world, and then my initials, SC. Super exciting stuff, right? What this means is that there's a whole new world of privacy use cases on the EVM or any other Cosmos chain using secret network smart contracts. You can encrypt any message of your choosing, any type of message, and then be able to decrypt that message in a secret network smart contract and then decide what to do with the data from there. If you want to go more in depth to the code itself, I highly recommend digging deeper into these repositories that we've been going through and actually looking at the functions and how they work. If you have any questions, just drop a comment on YouTube and me or somebody from the Secret Network Foundation team will be sure to get back to you. And also join Secret Network's Discord. We have weekly developer calls every Monday at 12 p.m. Eastern Time, where you can ask any questions that you have about secret contracts, EVM contracts, anything that you're building, just come here, ask questions, and there will be people who will be excited to help you out. Thanks so much for watching. I've been Sean Conrad, and we hope to see you for our next developer tutorial.